Here we have another example where we are asked to find the formula of a compound. They did not specify whether we have to find the empirical formula or the molecular formula of the compound. And to know the empirical formula of a compound, we need the percentage composition of the compound. We have seen that in previous examples. And if you want to know the molecular formula also, you need its molecular weight, also known as relative molecular mass of that compound. But here we are neither given the percentage composition nor its molecular weight. Instead, we are given volumes of different reactants and products measured during a chemical reaction. And using this data or information, we have to figure out the formula of the compound. How do we do that? Now let us look at the data given in the question. See, here we are asked to find the formula of a hydrocarbon. Hydrocarbons are compounds that contain only carbon and hydrogen and nothing else. So the formula of any hydrocarbon contains only these two symbols. Then have we already figured out the formula of this compound? No. To know the formula of this compound, we need to find out the subscripts of these two symbols. That is the challenge we have. And because we do not know the subscripts of these two symbols, let us assume them to be X and Y. So let us say the formula of this compound is CXHY. Now what else is given in the question? It was stated that 5 ml of this gaseous hydrocarbon was exploded with 30 ml of oxygen in a eudiometer. That is 5 ml of this CXHY was combined with 30 ml of oxygen. And you know the molecular formula of oxygen is O2. It is diatomic. And after the explosion, that is after the reaction got completed and everything again got cooled down to the room temperature. That's what this means. The volume of the gases remaining was measured to be 22.5 ml. So the first thing you need to understand is all these volumes are measured at the same temperature and pressure, and that is clearly stated in the question. But it was not given at what temperature and pressure these volumes were measured. But from the wording of the question, you need to figure out that these volumes are all measured at the lab temperature and pressure. Now I have a question. What are all present in these gases at room temperature? See, whenever a hydrocarbon burns in sufficient oxygen, it produces only two compounds, carbon dioxide and water vapor. So obviously at the end of the reaction, there will be some CO2 and H2O. And in addition to these two, there may be some leftover oxygen or this hydrocarbon. And it is given that addition of this concentrated solution of potassium hydroxide, the volume of the residual gas was reduced to 12.5 ml and contains only oxygen. So obviously there is some leftover oxygen. That means we carried out this reaction with excess oxygen. We have more oxygen than that is required to completely burn this 5 ml of gaseous hydrocarbon. So obviously all the hydrocarbon got burnt and there is some leftover oxygen. Of course, there will be some CO2 and H2O. But remember, because this volume is measured at room temperature, and at room temperature, because H2O is a liquid, this will not contribute to this volume. So this 22.5 ml of residual gas contains only carbon dioxide and oxygen. So you have to figure this out. Now, Addition of this concentrated solution of potassium hydroxide reduced the volume of the residual gas to 12.5 ml. You need to know the fact that concentrated solution of potassium hydroxide absorbs carbon dioxide. So when this solution is added, all the carbon dioxide present in this residual gas was absorbed, and the leftover is only oxygen, and it has a volume of 12.5 ml. Then what will be the volume of the carbon dioxide produced during the reaction? The total volume of carbon dioxide and oxygen together is 22.5 ml, and the volume of oxygen leftover is 12.5 ml. That means the volume of carbon dioxide produced is 22.5 minus 12.5 ml. So that is exactly 10 ml. So in this reaction, 10 ml of carbon dioxide is produced. Now if 12.5 ml of oxygen is left behind and 30 ml of oxygen is what we have started with, then what is the volume of oxygen that participated in the reaction? 30 minus 12.5, right? So that would be 17.5 ml of oxygen. So 5 ml of this hydrocarbon on complete combustion with exactly 17.5 ml of oxygen produced 10 ml of carbon dioxide, and of course some water vapor also. And we do not know the volume of this water vapor. And between these three volumes, the common factor is 2.5. And if we divide them with 2.5, then here we would have 2 ml of CXHY, 5 over 2.5 is 2, plus 17.5 over 2.5 is 7, so 7 ml of oxygen, and 10 over 2.5 is 4, so 4 ml of CO2, and of course some unknown volume of water vapor. Now you may be wondering where we are going with these calculations. See, our goal is to find the molecular formula of this compound. For that, we have to figure out the values of X and Y. But here we have the volumes of reactants and volume of one of the product formed in the reaction. So how do we figure out the values of X and Y from these volumes? For that, we take the help of Avogadro's hypothesis. And according to Avogadro's hypothesis or Avogadro's law, equal volumes of all gases when measured at the same temperature and pressure must contain equal number of molecules. That means if one volume of this hydrocarbon contains n molecules of that hydrocarbon, then one volume of oxygen must also contain the same number of molecules, and one volume of CO2 must also contain the same number of molecules of CO2. That is Avogadro's law, provided these volumes are all measured at the same temperature and pressure. And you know, if you divide the number of molecules with Avogadro's number, that is denoted by capital N, you would get the amount of substance, also known as the number of moles. So let us divide these with capital N. Then you would get N over capital N moles of CXHY, small n over capital N moles of O2, small n over capital N moles of CO2. See, here we have the same term small n over capital N in all these three cases. So that simply means if you have equal volumes measured at the same temperature and pressure of different gases, then they not only have the same number of molecules, they also have the same number of moles. That is, they have the same amount of substance. So we can state Avogadro's hypothesis or Avogadro's law as equal volumes of all gases at the same temperature and pressure contain equal number of molecules or equal number of moles. Let us say 1 volume of this hydrocarbon contains A moles, small a moles. Then 1 volume of oxygen must also contain small a moles of oxygen, and 1 volume of carbon dioxide must also contain small a moles of CO2. Here we have 2 ml of the hydrocarbon. In general, 2 volumes of the hydrocarbon. If 1 volume has A moles, then 2 volumes must contain 2 times A moles of this hydrocarbon. 7 ml of oxygen, or in general 7 volumes of oxygen, must contain 7 times A moles of oxygen, and 4 ml, or in general 4 volumes of carbon dioxide, must contain 4 times A moles of CO2. And A is common between these 3 terms, so if you divide them with A, you are left with 2 moles of this hydrocarbon combines with 7 moles of oxygen to produce 4 moles of CO2. And this is interesting. From the volumes of the gaseous reactants and products measured in the experiment, in the chemical reaction, we are able to figure out the number of the moles of the reactants and products whose volumes are measured in the chemical reaction. That is because of Avogadro's law. Now we can write a balanced equation from these numbers, that is 2 times CXHY, that is 2 moles of this hydrocarbon, and 7 times O2, 7 moles of oxygen, 4 CO2, that is 4 moles of carbon dioxide, and some amount of water. We do not know the volume of the water vapor produced, so obviously we do not know the number of moles of water produced in the reaction, so let us say it is P. And this is still incomplete because we do not know the value of this P. And according to John Dalton, atoms are neither created nor destroyed during a chemical reaction. That is, the total number of atoms of each element must be the same before and after a chemical reaction. And using this principle, we shall try to figure out the value of this P, X and Y. Let us see how. Before the reaction, how many carbon atoms are present? That is to the left of this chemical equation. How do you get the number of carbon atoms? Here the subscript for carbon is X and there is a coefficient 2 here, so you have to multiply these two, and carbon is present only here. This is all oxygen. So 2 times X is the total number of carbon atoms present before the reaction. How many carbon atoms are present after the reaction? Carbon is present only here. There is no carbon here. And the subscript for carbon here is 1 and there is a coefficient 4 here. So the total number of carbon atoms after the reaction or to the right of this equation is 4 times 1. So X is equal to 2. Now let us look at the number of oxygen atoms. There are 14 oxygen atoms. Oxygen is only present here. There is no oxygen here. So there are 14 oxygen atoms before the reaction. So there must be the same number of oxygen atoms after the reaction. Oxygen is present here and here as well. So here there are 4 times 2, that is 8 oxygen atoms. Here there is P times 1. The subscript for O here is 1. So there are P oxygen atoms here. That simply means P is equal to 14 minus 8 or 6. So we are able to figure out the number of moles of water produced in this reaction. We got 6 moles of water. Now what about the hydrogen atoms? On the left hand side, that is before the reaction, hydrogen is present only here. So that is 2 times Y. Hydrogen atoms are there before the reaction. And hydrogen is present only here after the reaction. There is no hydrogen here. So that is 6 times 2, that is 12. Therefore, y is equal to 12 over 2 or 6. So we are able to figure out the value of y as well. Then the formula of this hydrocarbon is C2H6. See, we are able to figure out the molecular formula of this hydrocarbon just by measuring the volumes of the hydrocarbon, oxygen and carbon dioxide involved in the chemical reaction. We are able to do this because of this powerful law known as Avogadro's law. And this is the molecular formula of the hydrocarbon. Then what is the empirical formula? To get the empirical formula, you have to divide the subscripts with the greatest common factor between them. The greatest common factor between these two subscripts is 2. And if you divide them both with 2, you would be left with CH3. So CH3 is the empirical formula of this compound and C2H6 is its molecular formula. We are able to do this because of Avogadro's law.